This example is going to compare the performance of the average and the switching model of the converter with the 100 megawatt wind plant example. So we're using the file wind3.ecf, and I'm going to, first thing is I'm going to right click on this wind plant circuit, and we're just going to show how you model that. I'm going to right click, and you can see that push into selection at the bottom, and it opens up a view of the sub-circuit that represents the power plant controller and the converter bridge. So you can browse through this, look at the power plant controller. That's interesting. But I'm going to right-click on the hardware, and I will push into that. And we see some DC bus over here on the left-hand side. And we look over here on the right-hand side, and we see some filtering before it interfaces to the grid. This block in the middle is interesting. This is a converter average model. So I'm going to right-click on that again. I'm going to push into that. And what we see, if you remember the lecture portion from the September 14th session, these are controlled sources on the AC side. And so we don't have switching inverters, but we have controlled sources here and here and here on the AC side. And if I go over to the DC side, I have a controlled current source here. So that implements the average model with the controlled current sources and voltage sources. So I'm going to back out of this, close all these views, and I'm going to double click on this component, which is means I want to edit it. And let me bring that into view. It's a big dialog box. So I'm going to click on the converter control. And what I want to do, this is the, again, it's a converter control tab, and I want to change this selection here. So what I'm going to do that is I'm going to change it over to the detailed plus generic model. And I do want to make sure that I'm using compiled codes for the data acquisition and the inverter control system. Whether I'm using the detailed model or the average model, this makes a big difference in the simulation time. So with that, I'm going to scroll down and find the OK button. It's out of the view of the video. But notice on the main schematic, my symbol changed from AVM to DM right there. And so now what I can do, I'm going to right click on this again, and I will push into that. And I'm going to right click on the hardware, and I'm going to push into that again. And here in the middle, notice it says converter 2 level where it said converter average model or something like that before. I'm going to push into that. And here, see some more things, but there's a PWM generating gauge signals, and it goes into this voltage source converter 2 level. And this may be the last time we have to push into that. But notice now that we see the 6 power electronic switches with looks like diodes numbers there. And so that's how you see the difference of implementation between the average model and the switching model in EMTP. When you get out to this first drilled in level, notice you can push into the converter control, and you can also push into the power plant controller. And you also see at the top level here the different interface transformers, the converter transformer, the Parker plant transformer, and then you have the equivalent collector grid in here. We should not be editing these directly. So I'm going to close that. And let's look at the simulation options. So this was set up for the average model originally. And so I was running at a 50 microsecond time step. Since I just changed it to the detail model, I'm going to change this to a 10 microsecond time step. That's better for the switching model, so it's going to capture the switching impulses. And then my ComTrade writer component was set up to write to AVM.CFG. So I'm going to double click on this. The sampling frequency before for the average model was 20 kilohertz. That's capturing every 50 microsecond time step. I'm going to change this to 100,000. There we go. 100,000 right there. And I would also go down here to the bottom, and I'm going to select a CFG file name, and I want to type DM for detailed model. And it's going to ask if I want to overwrite that because I've run this before. And I want dm.dat here. And this is going to set up so when you run this yourself, the Jupyter notebooks are going to be pointing at the correct files on disk. So again, we have dm.cfg and dm.dat. And then back at the top, I didn't change any of the channel definitions or anything, but I do want to have my sampling frequency to match the time step, so I get every simulation data point saved to the ComTrade file. So I will click OK there. We're going to run this case twice manually, and I won't do that now, but what I will do is switch over to the Jupyter notebook where this case is ready to analyze. So you use the notebook.bat, actually notebook3.bat utility to start up this notebook. You can see plot3 in the name in the top of the window inside your browser. These are service functions. I'm going to load, define some functions to import the ComTrade library, the function that loads the channels. We've used this before. I'm going to stick with matplotlib, and I'm going to it defines a function. So we're skipping over the PSCAD. We're going to click this cell here to define the to import the data from the EMTP simulations. So there's a couple of those, and with any luck, it will import those. It's taking several seconds, I think, because I have several Jupyter notebooks open. But there it read, these are 6-second simulations, so it read the data from both files, the detailed model here and the average model here. Not as many points from the average model because of a longer time step. I'm going to, you can show the case plot for the switching model and the average model. I'm going to skip over that right now just to show the comparison plot between the two cases. And so if you look at the RMS voltage, the power, these are pretty close between the two. So it says in these top level performance criteria, there's a lot more variation, harmonics evident in P and Q with the detailed model, but the general trends are pretty similar. So you could often do dynamic simulation studies, interconnection studies with the average model and save some simulation time. But there is a difference in the harmonics. So I'm going to go down to this next cell where we're importing from SciPy the FFT package. So let me do that. It takes a while to import SciPy, and actually it ran the analysis. So I'm going to go back over and what all the Python code does. But what I have is a snapshot here, a window of about 3 cycles of one of the grid currents. I think it's IA, the phase A current. Let me zoom in a little bit on one of these, and you'll be able to see close up that there's a lot more harmonic content in the detailed model in blue. So I have this is the harmonic spectrum. It is the fundamental and the peak is at 60 hertz, but there's a lot more harmonic content. That's a semi-log scale in the detailed model current. We have some numerical outputs. The fundamental peak and the fundamental RMS are pretty close for the detailed and the average model. You do get a difference in total harmonic distortion, 6.5% in the switching model, and 0.01% on the average model. So if you're trying to look at harmonics, you wouldn't see those in the average model. That harmonic content is a little high, so maybe a better job on the filter design would do a better job there. But the code that ran this, this function here makes a slice of 50 milliseconds or 3 cycles, or maybe it's 6 cycles. I have to double check that. This is the function that does the FFT. So there is FFT, taking the input signal Y, that's defined from the SciPy package. This FFT freq function gets the the sample rate, the sampling in frequency domain compared to the time domain. So it's taken the the number of sample points in the FFT, capital N, and the time step dt to figure out what's a step in the frequency domain in hertz. This next line gets the absolute value, the magnitude, which we're interested in. The phase information is available, but we don't. We're not really interested in that with the harmonic distortion. We're also taking out the scaling by n. If you do the signal processing FFT, they normalize it by 2 over n, but that is not what we're really interested in for power systems work, where we're really interested in the power in the harmonic distortion. And so these are just NumPy functions that with vector arithmetic we can pick out the peak and the RMS magnitude of that peak, and that's going to be at 60 hertz. And so I should say, in the FFT and SciPy, you can do what's called a mixed radix FFT. So you can do it on exactly 1,000 points or 2,000 points. So you don't have to necessarily apply windowing to the time domain data before you do the FFT on it. So we can do it on exactly 1,000 points and not a power of 2. We're not limited to like 1024 or 2048 points. These are NumPy functions that get the total RMS. Literally doing the sum of the squares, taking the average of that, dividing by 2, so we get the the RMS. And then the total harmonic distortion, so we get the total RMS minus the fundamental RMS, take the square root of that, and divide it by the peak RMS to get the total harmonic distortion. And those are our numerical outputs here. For the 6.5%, and you can also see visually that there's a lot of higher harmonics, and you don't see a prevalence of, if you look at this, the harmonic spectrum here is pretty flat, right there. So you don't see, for example, you don't see a noticeable fifth harmonic, or that'd be the fifth, the seventh would be about right there. You don't see that. You see a dispersion of the harmonic frequency magnitudes.